7.5 Operations with matrices. So we can represent matrices a few different ways. It's standard convention to really show it these three different ways. So we can either take a matrix and write it as just an uppercase letter. We might call it A, or matrix B, or matrix C. We could also take a matrix and write it instead by a representative element in brackets. So here we see the brackets around the element A, ij, and the element B sub ij, and the element C sub ij. Or we can have a matrix that is denoted by the rectangular array with all of its terms in there, and we've seen this. This is what we've been working with to solve systems. So it's that array that we've seen so far, but we will see really these variables get used the most often. All right. So two matrices, here we have matrix A and matrix B, are considered equal when they have the same dimension and all of their corresponding entries are equal. So in this example, we want to solve for the first term, or that term in row 1, column 1. That's what the double letters stand for there. Row 1, column 2, row 2, column 1, and row 2, column 2. So when I'm saying this is A, this is the row first, and then it's the column. Okay. So if we are saying these matrices are equal, then we're just saying that the numbers in the same position are equal. So the term in the first row and the first column is 2. The term in the, let's color code this, the term in the first row, second column is -1. The term in the bottom left is -3. And the term in the bottom right is 0. Nothing too complicated here. All right. So we can use these rules to help us eventually solve, but also to do some basic operations. So one of the operations we can do is called matrix addition. And when we have matrix addition, we need to make sure that our matrices are the same dimension. If they are not the same dimension, then this really is not possible. So they have to have the same dimension here. In order to do this, we're just going to add the numbers that are sitting in the same position. So to find the sum in example A here, we're just going to add the numbers that are in the same spot. So when we do this, we will have -1 plus 1 in that first spot, and -1 plus 1 is 0. In that top right spot, we have 2 plus 3. That's going to give us 5. In this bottom left spot, we have 0 plus -1. It's going to give us -1. And in the bottom right, we have 1 plus 2. It's going to give us 3. And we have our solution. All right. Take a look at the next one. So again, we have the same dimensions here, and we want to make sure that when we go to add these, we end up with a matrix that has the same dimensions. So row 1, column 1 plus row 1, column 1 is going to give us 0. Row 2, column 1, row 2, column 1 is also going to give us 0, and row 3, column 1, and row 3, column 1 actually also gives us 0, and that's okay. No big deal. It's just a matrix of zeros. All right. So here we are basically asking just to add these together, but we are given it more in this variable form. So we're going to call this matrix A, this matrix B, and they're asking us to add these two together. Well, we have a problem. The sum here, A plus B, is considered to be undefined, and it's undefined in this case because my matrices are not the same dimension. So I wouldn't have enough numbers to add together. When I start to do this, I'd try to do 2 and 0, 1 and 1, but then 0 would go with who? I don't have anybody to pair up with it, so I cannot get an answer here. So my answer is considered undefined. Another operation we can do is called scalar multiplication. And what a scalar is, think like on a scale, if you were to take an image and put it into, say, Google Docs, and you were to scale the size of it, you're just expanding it all by a certain amount or making it smaller by a certain amount. So what we are doing is just, well, basically like when we multiply a row to reduce it, we're just multiplying all of the rows to either reduce it or make it larger. So scalar multiplication is just going to multiply every entry by whatever number you put on the outside. So in this first example, we want 3 times matrix A. So what we're really saying is we want to do 3 times this matrix. All we are going to do, and it's very simple. It sounds like it should be more complicated, but it's really not. In order to do this, we are literally going to take every one of those numbers, the 2, the 4, the -3, the 0, the -1, the 2, the 1, the 2, and we're going to multiply every one of them by 3. I mean, it's that simple. It seems like it should be so much more complicated, but we are literally just multiplying every one of these numbers by 3. Whatever my scalar is, I'm just going to multiply. So that's going to give us 6, 6, 12, -9, 0, -3, 6, 3, 6. All right. We can also write the symbol -A, and what that's really saying is the negation of A, or we can think of it as the opposite of matrix A. And all we're doing is just changing the sign. It's like multiplying by a -1. So if A and B are the same dimension, then A minus B is really the same thing as saying A plus -1 times B. And that's going to help us to get our answer a little easier here. The order of operations for matrix expressions is similar for real numbers. So if you are asked to multiply and then add matrices together or something along those lines, you do need to make sure you are following that order of operations. So PEMDAS does come into play here. All right, so we want 3A minus B. So we're going to do 3 times matrix A. Matrix A is 2, 2, 4, -3, 0, -1, 2, 1, 2. And then we want to subtract matrix B from that. So that's 2, 0, 0, 1, -4, 3, -1, 3, 2. Okay. You can think of this as 2 different things going on here. I can either just think of each entry and say, okay, it's 3 times 2 minus 2, and just work that way. Or I could work this out in steps, and it really doesn't make a difference. All right, so we could work this out in steps, and really scalar multiplication is like the distributive property. Literally everything is going to get multiplied by that 3. So I don't need to write it all out here. I just need to know what's going on. So when I do multiply, that's going to give me 6, 6, 12, -9, 0, -3, 6, 3, 6. And to that, I am going to subtract, matrix B. So minus, or I can think of that as plus negative matrix B. So however you want to do this, it really doesn't make a difference. Let's see, 2, 0, 0, 1, -4, 3, -1, 3, 2. All right, so now I just want to subtract those numbers to get my final answer. So I'm going to say 6 minus 2 is 4. 6 minus 0 is 6. 12 minus 0 is 12. -9 minus 1 is -10. 0 minus -4 is +4. -3 minus -3 is -6. 6 minus -1 is 7. 3 minus 3 is 0. And we have 6 minus 2 is 4. And there is my solution. We also have some properties for matrix addition and scalar multiplication, and they're very similar to just those rules for real numbers. For example, if I were to have a scalar of 1, it's the identity. It's not going to change it, right? Like multiplying by 1 does nothing. Or if I were to add a 0 matrix, we could call it O for 0 matrix. Then it's like adding nothing. That's the additive identity. Nothing changes. I can add in any order. That doesn't change anything. The distributive property holds. Basically, any property with real numbers is going to work exactly the same way as it does with real numbers n matrices. So let's show one of those properties here. You're going to use the distributive property. So we could either add these matrices together and then multiply by 3, or I could multiply these matrices by 3 first, and then I could add them together. It doesn't make a difference. I should get the same answer either way. So let's see it. Why don't we do both? So first, why don't we try adding? We'll do 3, and we'll add these guys together. So negative 2 plus 4 is 2. 0 plus negative 2 is negative 2. 4 plus 3 is 7, and 1 plus 7 is 8, and then we'll multiply. So that is 6, negative 6, 21, 24. All right, so here I added first and then distributed. Okay, we could distribute first. Okay, so that's going to give us negative 6, 0, 12, 3, plus 12, negative 6, 9, 21. And then we can add. And that's going to give us negative 6 plus 12 is 6. 0 plus negative 6 is negative 6. 12 plus 9 is 21. And 3 plus 21 is 24. So regardless, we get the same answer. Either way works. The property holds. It kind of just depends what you're looking to do. Whoops. Oh, let me go to the next page. There we go. So in that last example, we could have done it either way. We could add and then multiply, or multiply and then add. It's not that we're changing the order of operations. We're just using the distributive property. The algebra of real numbers and the algebra of matrices are going to have a lot of similarities, as you can see here. When we're doing a equation, we can solve an equation using the inverse operations to undo each other. So if I am adding two matrices together and then it equals another matrix, I can subtract one matrix to the other side, or technically add the negative. And that's going to, fix the solution here. So here we want to solve for x. We don't know what matrix x is, but we want to solve for it. So we have 3 times matrix x plus a is equal to b. So 3 times matrix x plus a is equal to b. Now, what I would recommend with problems like this, deal with the equation as if it was algebra first. Solve for x means get x by itself. So that's 3x plus a is equal to b. I would subtract a from both sides. Okay, so why don't we start with this? All right, so from there, to get rid of the 3, we would multiply by a third on both sides. It's really dividing by 3, but that's multiplying by 1/3. So we have 1/3 b minus a, and that's going to give us our matrix. So x is going to equal 1/3 times b, which is negative 3, 4, 2, 1, minus a, which is 1, negative 2, 0, 3. Again, we could do the distributive property first, or we could subtract. It doesn't matter. I'm going to subtract first. I think it'll be a little easier. All right, so we have negative 3 minus 1 is negative 4. We have, let's see, 4 minus negative 2. That's going to give us 6. 2 minus 0 is 2, and 1 minus 3 is negative 2. Last but not least, I'm going to multiply everything by 1/3. So that's going to give us negative 4/3, 2, 2/3, and negative 2/3.